When throughput demands exceed single-thread capacity, Kafka consumer groups become mandatory. A consumer group ensures that each message partition is read by exactly one consumer instance within that group. This one-to-one mapping between partition and consumer instance is the fundamental mechanism for parallel scaling. If a topic has 8 partitions, the group can scale up to 8 active consumers before instances become idle. Adding a 9th consumer instance to the group provides redundancy but yields no further throughput gain. The group identifier, defined by the group.id configuration parameter, dictates which set of consumers coordinate their offset commits and partition assignments. Misconfiguring this identifier leads to message duplication across processing pipelines, a common integration error. The broker manages the assignment process using the group coordinator, ensuring fault tolerance and dynamic scaling when instances join or leave. Choosing the correct partition assignment strategy directly impacts load distribution. The default, range assigner, works by sorting partitions numerically and consumers alphabetically, then assigning contiguous blocks of partitions. This often results in uneven distribution, especially when the number of partitions is not perfectly divisible by the number of consumers. The round-robin assigner distributes partitions sequentially across all consumers, aiming for better balance, but it ignores existing assignments during rebalances. For stability, the sticky assigner is preferred. It minimizes partition movement during rebalances, ensuring that consumers retain as many of their previously assigned partitions as possible, thereby reducing processing disruption and cache invalidation overhead. Always evaluate the sticky assigner first for production environments requiring high stability and minimal rebalance impact. Consumer group stability hinges on timely heartbeat submission and message processing. The session.timeout.ms parameter defines the maximum time the broker waits for a heartbeat before declaring a consumer dead and initiating a rebalance. Typical values range from 10 to 30 seconds. Crucially, the max.poll.interval.ms defines the maximum duration allowed between successive calls to the poll method. If message processing takes longer than this interval, the consumer is evicted, triggering an unnecessary rebalance. For long-running batch processing, increase max.poll.interval.ms significantly, perhaps to 5 minutes, but ensure the consumer thread remains responsive. A rebalance event forces all consumers in the group to stop processing, commit offsets, and renegotiate partition ownership, causing temporary service interruption. Achieving true parallelism requires understanding the consumer-to-partition relationship. A single consumer instance must process messages from its assigned partition sequentially. To maximize throughput, the number of consumer instances in the group should ideally match the number of topic partitions. If processing is input-output bound, you can implement multi-threaded processing within a single consumer instance. This involves the consumer polling messages, then immediately submitting them to an internal thread pool for asynchronous processing. However, offset management becomes complex, requiring careful synchronization to ensure offsets are committed only after all messages in a polled batch are successfully processed by the worker threads. Never run multiple consumer threads sharing the same Kafka consumer object. This violates thread safety and leads to unpredictable behavior.
Relying on automatic offset commitment where enable.auto.commit is true risks data loss or duplication if the consumer crashes mid-processing. For guaranteed delivery semantics, set enable.auto.commit to false and manage offsets manually. The commit sync method blocks until the broker confirms the offset commit, providing strong guarantees but potentially impacting latency. Alternatively, commit async returns immediately, allowing faster processing, but requires implementing a callback handler to manage transient errors during the commit attempt. When committing manually, always commit the offset of the next message to be consumed, which is the last successfully processed message offset +1. Commit offsets frequently enough to minimize reprocessing time after a failure, but not so frequently that it overwhelms the broker's transaction log. A poison pill message, one that consistently causes processing failure, can halt an entire partition if not handled correctly. The consumer must implement a robust try-catch block around the processing logic. Upon failure, instead of retrying indefinitely, the message should be immediately routed to a dedicated dead letter queue topic. This requires producing the failed message to the DLQ topic before committing the offset of the original message. This ensures the consumer can advance its offset for the main topic partition, preventing the poison pill from blocking subsequent messages. The DLQ topic should be monitored by a separate, slower consumer group designed for manual inspection and remediation, maintaining separation of concerns between high-speed ingestion and error handling. Different downstream systems often require distinct processing speeds or transformation logic from the same source topic. Using separate consumer groups for each application ensures complete processing isolation. For example, a high-priority real-time dashboard might use Group A, while a low-priority batch analytics job uses Group B, both reading from the same topic. Since each group maintains its own independent set of offsets, a failure or slow processing in Group B will not impede the performance or offset advancement of Group A. This isolation is critical for microservices architectures, where service degradation must be contained. Always use descriptive, unique group.id identifiers reflecting the application and environment, such as inventory service-processor-production. Traditional dynamic membership forces a full rebalance whenever a consumer instance restarts, even briefly. Static membership, introduced in Kafka version 0.11, mitigates this overhead significantly. By configuring the group.instance.id parameter, you assign a persistent, unique identifier to each consumer instance. When an instance restarts, the group coordinator recognizes the instance ID and attempts to reassign the exact same partitions it previously owned, bypassing the full rebalance protocol. This dramatically reduces the time spent in the rebalanced state, improving application availability during rolling deployments or planned maintenance. Static membership requires careful management of instance IDs to prevent conflicts, ensuring that no two running instances share the same identifier. System analysts must prioritize 5 key parameters for robust consumer group configuration. First, fetch.min.bytes controls the minimum data size the broker returns, optimizing network efficiency. Second, max.partition.fetchBytes limits the maximum batch size per partition, preventing memory exhaustion in the consumer. Third, auto.offset.reset must be set to either earliest or latest to define behavior when no committed offset exists, typically earliest for data integrity. Fourth, ensure heartbeat.interval.ms is correctly set to 1/3 of the session.timeout.ms value for timely liveness checks. Finally, always verify the isolation.level is set to read.committed when interacting with transactional producers, guaranteeing that only successfully committed messages are consumed, preventing reading of aborted data.